And note that we don't have any more light anymore here because it's all been absorbed for the most part down in the UV region. So the first thing to note is that there is a nice baseline region right at 500 nanometers. So what we can do here is peg that to 0 because we don't want that to jump around. Notice if I can, I'm going to kind of move the cuvette around a little bit. Well, I can't really see it too much. Oh, there you go. Yeah, see how I can, like, by moving the cuvette, kind of move that around a bit? We don't want that to happen. So let's go ahead and take a subrange and peg that to 0. Like we talked about, this is the equation that was built by the wizard. So we're going to go ahead and go to basic math. And I'm going to actually turn this off for a second. So we're going to go to, advanced math, array math, and do a subrange. Because this multiplier block is the final absorbance output. All this is doing then is going into a unit labels node and then our graph output, which is right there. Pardon me. So we're going to do a subrange of about 500 to 503 nanometers. We hit apply. Look at that. So now we can see that's our it's noisy, but that's an array value. If we were to make this the same value, note that it makes it a scalar, a single unit. Now that's important for the next thing we're going to do because you can do mathematical processes on a scalar single value, but on an array of values like this, you're going to have to reduce that down to a single value, and you can do that with an average block. So check this out. We're going to go ahead and connect that to an average block. And now this is the average of that 500 to 503 range. And this is what we want to subtract out from everything else, right? So let's go ahead and do basic math and subtract. And we're going to do our main feed minus that. And that's our new baseline corrected view. So let's get rid of this. I can do that. And let's connect it to here. Bam. And notice that now this is pegged to 500 nanometers. And it'll always stay there. So we can kind of clean up our view a little bit. There we go. Now, I had done before this so we can either use the 400 nanometer or something out here to do this concentration analysis. I had done this in Excel, so hopefully you can see this. And this is showing the different concentration levels, 30, 40, 60, and 80 grams per liter. And we get really nice growth here, just as like textbook quality. And then we get this classic plot showing absorbance versus concentration. And we get a really nice 0.9997 R squared linear fit. Perfect, right out of a textbook. But this isn't what we really want. This is great for your high school chemistry homework to do absorbance versus concentration, but we want the opposite of this. We want concentration versus absorbance because our input, our x value, is going to be this, and our output, we want to be concentration. That's our y. So we know that 114.7 times the absorbance at 723, that was the correlation I had used right there, that's going to give us a really nice nickel concentration value. So let's go ahead and build that in. So if we go ahead and take another subrange. So we're going to go to advanced math, array math, subrange. And we're going to do 723. So we're going to pull off of our baseline corrected feed. Let's just do 723 to 723. And that's our value right there, which is, you can see, is 0.69 and then about 0.7 right there. So that's what we're looking for. Now we want to have our constant block. So let's do a constant. We said 114.7 if I recall, 114.7. And let's multiply those together. Zip those together. Let's add a label block. Now check this out. You can right click and also duplicate things that already exist. So I'm just going to duplicate that same unit block, bring that over there, and then one of our view options, you have graph, scalar, table, or a color view. We want a scalar value. So let's bring that and look at that. Now let's change these units because we don't want that. We want that to say NiCl2 concentration, and the label there is grams per liter. Now that's great, except the units are, look at all those decimals. That looks pretty messy, right? So let's go in and clean that up. Let's go to unit precision, dial that down to maybe 2. That looks a little better. Right, now there we go. Now we have a nickel chloride concentration monitor. Let's take some of our other solutions here. So let's pop in one of our 30s. So here's a 30. Throw that in. Look at that, 29.6. Looks pretty good. Let's throw in one of our 40s. 39.98, 40 right there. Let's throw in one of our 60s. There's a 60. And there's 60. So now we're very quickly getting an answer about these solutions that is very important for this nickel plating process, so we can quickly adjust the dilutions. Now, real quick, let's say that this is a good way, if you've already done the analysis and you know what this coefficient is, to put this in. But let's say that you've got like a huge calibration regression and it's updated very regularly. You don't want to deal with putting in just a constant value like this. So let's get rid of this. We're going to feed in an external file. So check this out. This is a file with those same values that I created. So this is only 5 points, but this could be 500 points if you had a big calibration list, let's say, of data. And we're going to feed this in using what's called the linear regression tool and the function evaluator. So one of our sources options is going to be, so we can do a data source. The black body simulator is really cool. We won't have time for that, but if you get a chance, play with that. And then what we're going to bring in is the file. So now let's go to advanced math, array math, and linear regression. Let's bring in that file we had mentioned. Hopefully yeah, OV webinar. So that was our nickel cow. And see, that was that line that the data set had characterized or drawn there. So that was the values from that file. We're going to bring it into a linear regression. And we're also going to bring in in array math here, a function evaluator, evaluate function. We're going to bring that in. And before we connect these, I want to show you what this is going to do. So in the linear regression, you can set the order of this. First order is just linear, right? Or you can bring it up to 9, actually, 9-order polynomial. So let's say we're fourth order. It's going to do that fit and give you coefficients for all those. Or if you don't peg the intercept to 0, it'll also give you a non-zero value for this first coefficient. But we want that. We want this to be down to 1. And notice that we're back at 114.7, just like we had with our K block, right? So now if we plug this into here and this into here, let's see if we pop in our 60 again. Ta-da, there we go. So now think about what we've done here with this. We have successfully created a nickel chloride concentration monitor that has active baseline correction built into it. So if there's any shifts in the optics or so on, it corrects for that. And the ability to load in an external calibration file here from a source that you may be updating with some other protocol in your process or whatnot. So you can build these very quickly. And we did this in like 15 minutes. This would have been, you know, a bunch of money probably from a custom engineering firm if you had presented the same thing. But we want to give you the tools to do this stuff very easily yourself.